Welcome to another PocketCFI video from our series Secrets in Flight Theory. In today's video we will discuss the lift formula and how to really apply it and how it relates to your flying. The lift formula consists of the coefficient of lift, rho, a Greek symbol that in this case stands for density, the velocity squared, and the surface of the wings of the airplane. The reason the lift formula is so important and the way we like to teach it is because it gives you an overview of how your control inputs in the airplane affect lift. Think of the lift formula in terms of what can I control during flight. The coefficient of lift is your angle of attack. If you increase it, lift increases. If you decrease it, lift decreases. Rho is the density of the air molecules around you. There is no way for us to control them during flight, we can only calculate them. V squared is our velocity. We can control that by adjusting our power setting. And the surface of the wing is static. However, we can set flaps to increase our surface or to decrease our surface during flight. Additionally, our control inputs interact with each other. Let me demonstrate. Let's say you are in level flight and you're deciding to increase your angle of attack. Due to that, you are going to also increase induced drag, and the aircraft's velocity is actually going to decrease even though you did not change your power setting. Therefore, we are creating an initial increase in total lift, which will then be followed by a nose drop and an actual decrease in lift, corresponding to our lecture on stability. Similarly, if we decide to increase our velocity by adding power, and we do not do anything to our angle of attack, our airplane is going to produce lift. It is going to start climbing. As it climbs, the angle of attack starts increasing. As the angle of attack starts increasing, what is going to happen? We are again going to produce induced drag, and our velocity is actually now slowly going to start to decrease. Once again, bringing into effect our stability. Let's come back to density for a moment. Density is important because the air molecules around our airplane are interacting with our airfoil. Therefore, the more air molecules are present at one given time, the more interaction there is with our airfoil. For example, in denser air, you can say that each of these little circles represents an air molecule. This is very simplified, of course. But we can say that in this chunk of air that we are currently flying through, we have 3 by 3 air molecules, while in another chunk of air that is less dense, we only have 2 by 2. What happens when we fly through the denser air? More air molecules are interacting with our wing, thereby creating a stronger Bernoulli principle, thereby producing more lift inherently. The less dense air has less air molecules that can interact with our airfoil at one given time, and therefore in less dense air, our airplane produces less lift. This is very, very obvious when you take a small training airplane and you climb it to a higher altitude. Your airplane's climb performance will decrease and decrease and decrease until it gets to a point where it can actually no longer climb and can only maintain altitude. You can download all of our books and references used in our videos from our website and from our app. Our membership and materials are both for free. Sign up, and from the Access portal, click on Aviation Training Materials to find a list of all the books and references that we offer. Find the book you are looking for, click on the book, wait for it to load, and either read it in your app or browser or download the PDF file directly to your computer or device. Thank you.